Hi everyone. So today we're going to wrap up Chapter 3 or start to wrap up Chapter 3 for Module 2. So we're going to talk about changes of state. Now, last time we talked about energy and how matter absorbs energy. And now we're going to apply that to matter that can undergo changes of state. So we've also previously talked about solids, liquids, and gases. Now, if we imagine water as a solid, that's ice, and as you add heat to ice, it turns into a liquid. And if you add even more heat, eventually that liquid will turn into a gas. So we'll talk about all of those different states. All right. So let's talk about the change of state from solid to liquid. So a substance is melting when it changes from a solid to a liquid at its melting point. Now, the opposite process is freezing. So a substance is freezing while it changes from a liquid to a solid at its freezing point. So water has a freezing/melting point of 0 degrees Celsius. So at 0 degrees Celsius, a solid is turning into a liquid or a liquid's turning into a solid, depending on which direction you're going. So if you're adding heat, it's melting. If you're subtracting heat or removing heat, it is freezing. And melting and freezing are reversible processes. So theoretically, we could take a piece of ice and melt it by adding heat, and then we could cool it and turn it back into ice if we remove heat. Now, there is a value called a heat of fusion, and that's associated with melting and freezing. So the heat of fusion, zoomed in a little too far there. The heat of fusion is the amount of heat released when 1 gram of liquid freezes at its freezing point, but it's also the amount of heat needed to melt 1 gram of solid at its melting point. So, for example, let's say that we are heating up an ice cube. So we're adding heat. The amount of heat needed to melt that ice cube, let's say it's 1 gram. The heat needed to melt is the heat of fusion. Or let's say we have a little puddle of water and it's 1 gram. And let's say we're cooling it, so heat is being released. Then the heat released is also the heat of fusion. So we're cooling it down into ice. All right, so for a given amount of substance, the heat that's released during freezing is equal to the heat needed during melting. So if you have 1 gram of a substance, whether it's a solid or a liquid, the amount of heat that's needed or released, depending on the process, is the same. And that's your heat of fusion. Okay, so let's look at some actual values for this heat of fusion. So in order to melt water or ice, so we'll put ice here in parentheses, we have solid water, and this little S in parentheses next to H2O indicates that we have a solid, so that's ice. We can add 80 calories per gram of heat, or 334 joules per gram of heat. So these are just two different units. In chemistry, we tend to use joules more so than calories. So this is used more often in chemistry. So if we add 334 joules of heat for every gram of ice, eventually we'll end up with water that is a liquid. So that L in parentheses stands for liquid. Now, to freeze water, we have to remove heat from the liquid water. So we're starting with liquid water, and we want to end up with ice or solid water. So we're going to remove 334 joules of heat for every gram of water. All right, now we can also write these values as conversion factors. So if we use the 80 calories per gram of water, we could write that with 80 calories in the numerator or the denominator. Same for the value in terms of joules. We could put 334 joules in the numerator or the denominator. It just depends on what unit we're trying to get rid of and which unit we want to end up with. So there is an equation that we can use to calculate the amount of heat needed to melt ice or the heat that's released when we freeze liquid water. So that's shown down below. So heat is equal to the mass of the liquid or the solid times the heat of fusion. So remember, the heat of fusion will be different for different substances. So if we were working with, let's say, ammonia, which is in cleaning products, that would have a different heat of fusion value than water. But typically we're looking at water. So let's do a quick learning check. How many joules are needed to melt 32 grams of ice at 0 degrees Celsius? All right. So joules is referring to heat or energy. And then we have our mass of 32 grams, not degrees Celsius. So let's write out what we're given. Now we are told the temperature, which is 0 degrees Celsius, but we're not actually going to use the temperature here. The temperature just tells us that we're at the melting or freezing point of water. Okay, so we need to determine how much heat is needed to melt this amount of ice. So our plan is to use that heat of fusion. So remember, we just saw that we can calculate the amount of heat needed to melt ice or freeze water, depending. We can calculate that by setting it equal to mass times heat of fusion. Okay, so let's plug in what we know. So we know the mass is 32 grams. And we saw that the heat of fusion is 334 joules per gram. So if we go out to the last slide, remember, we said that the heat needed to melt or freeze water is 334 joules for every gram. Okay. So let's make sure our units cancel to give us what we need. So we have grams in the numerator and the denominator. So that will leave us with joules, which is exactly what we're looking for. Okay, so I've got my calculator. I'm just going to do this quick calculation. Let's see, we've got 32 times 334. Okay, so I get 10,688 joules. But what about sig figs? So always remember to figure out sig figs here. How many sig figs does 32.0 have? 3. Remember that 0 at the end is after a non-zero digit and a decimal, so there's 3 sig figs. What about 334? How many sig figs does that have? 3. That one's easy. They're all non-zero digits. Okay, so that means that since we're multiplying these two numbers, our final answer should also have 3 sig figs. And that 0 there that's underlined, that is in between two non-zero digits, so it is significant. Okay, so there's a couple of different ways that we could write this in order to give it 3 sig figs. So we could write 107 because the first digit we're dropping is an 8, so we have to round up. And then we can put 2 placeholder zeros next to that so that we still maintain 10,000 joules. We don't have 107 joules. That would be a false answer. Or we could write this in scientific notation. So let's put a little invisible decimal at the end here. And I'll do it in green. So what would our coefficient be for scientific notation? 1.07. So remember, our coefficient is always in between 1 and 10 or equal to 1. And then how many times do we have to move our invisible decimal to get to that point? So 1, 2, 3, 4 times. So then we have our power of 10 and the exponent is 4. And this is a large number, so the exponent is positive. So this would be 1.07 times 10 to the 4th joules. Okay, so that's how much heat it takes to melt 32 grams of ice. And then here are the solution slides. And it steps you through all of the same things that we just did. So now let's talk about another change of state. And this one is really interesting. So there are some cases where instead of a solid turning into a liquid, sometimes a solid can go directly to the gas state. And this is called sublimation. So if you have a solid and you're adding heat and it turns into a gas, that's sublimation. There are also cases where a gas, when it's cooled down, will turn directly into a solid. And that's called deposition. So when sublimation occurs, the particles on the surface of the solid change directly to a gas. And during this process, there is no change in temperature. So the temperature is constant during this process. And that's the same for any change of state. The temperature will just remain the same. Now, when deposition occurs, gas particles change directly to a solid. Now, a really good example of sublimation, if you've ever used dry ice, maybe you used it at a party or to make some cool smoke effects. Dry ice is just solid carbon dioxide. Which is CO2, carbon dioxide. And you might have noticed that it never goes through a liquid phase. It always goes from solid to gas. So that's sublimation. Now, sublimation and deposition are reversible processes, so similar to melting and freezing. So the amount of heat needed to turn dry ice into a gas is the same heat that's released when the gas turns back into a solid. All right, so now for the last change of state, evaporation, boiling, and condensation. So water evaporates when molecules on the surface gain sufficient energy to form a gas. And then water condenses when gas molecules lose energy and form a liquid. So for instance, maybe before you've seen a puddle sitting out in the street, and then during a hot day, that puddle slowly disappears. And that's because heat is being added to the puddle of water, causing it to turn into a gas and rise up into the atmosphere. Or maybe you've also seen condensation on the windows of a car or a house, and that's just due to water molecules in the air cooling down and then depositing onto the surface of the window. So during evaporation, molecules of the liquid are converted to gas at the surface of the liquid. So if we had, let's say, a container that was closed. So this is actually called an Erlenmeyer flask, although my drawing does not do it justice. And let's say we had a little stopper in there and some water. And then let's say we heat that up. Water molecules on the surface of the liquid will rise up and become a gas. And then let's say we cut the heat off of the water. Eventually the gas molecules will sink back down and condense. So they'll turn back into a liquid. Now, when water is boiling, that's slightly different. So the water molecules acquire enough energy to form a gas or vaporize, and bubbles of water vapor will appear throughout the liquid. So during boiling, molecules of the liquid are converted to gas throughout the liquid as well as at the surface. So let's say we had that same flask of water, and we added enough heat for the water to boil. Water vapor will actually form everywhere in this liquid, so at the surface and throughout, and those can pass up and become gas molecules. So if you've ever boiled water on a stovetop, maybe you're making pasta or tea, you might notice bubbles forming on the bottom of your saucepan or your pot, and then kind of rising up to the surface. So that's boiling, whereas evaporation only occurs at the surface of the liquid. Okay. So that brings us to another value called a heat of vaporization. So remember when we were talking about melting and freezing, there was a certain amount of energy needed in order to melt a solid. And here, as we're going from liquid to gas, so either vaporization or condensation, there's a certain amount of heat needed to vaporize a liquid. So the heat of vaporization is the amount of heat that's absorbed to change 1 gram of liquid to gas at the boiling point. It's also the amount of heat that's released when 1 gram of gas changes to a liquid at the boiling point. So when we add heat to a liquid, that's vaporization. When we remove heat from a gas, that's condensation. And these again are reversible processes. So similar to what we saw with the other changes of state. Okay, so what is that value for water? So the heat of vaporization for water, which occurs at a boiling point of 100 degrees Celsius, is the heat absorbed when 1 gram of water changes to steam, or gaseous water. So if we start with liquid water and add 2,260 joules of heat per gram, we end up with a gas. And so that little g in parentheses means gas. And then we can also look at the reverse process. Let's say we have a gas and it's condensing. So we start with a gas and we end up with a liquid and we release 2,260 joules per gram. So again, we can write these as conversion factors. If we're considering the value in calories per gram, we could put 540 calories in the numerator or the denominator. But remember, in chemistry, we're typically going to use joules. So we can write 2,260 joules in the numerator or in the denominator, depending on what we're solving for. Okay, so let's do a practice problem. How many kilojoules, kJ, are released when 50 grams of steam from a volcano condenses at 100 degrees Celsius? Okay, so we're given a couple of values here. So we're told the mass of steam, so that's gaseous water, and that mass is 50 grams. And we need to determine how many kilojoules of heat are released. So that's going to occur during condensation. So the gas is turning into a liquid, so it's cooling down. So our plan, we're going to use that same equation we used in our last practice problem. But this time, instead of the heat of fusion, we're going to use the heat of vaporization. Okay, so very similar to that last problem we did, but this time we're talking about condensation. Oh, and I should mention, we are given the temperature that this occurs at, but we don't have to use the temperature because it actually stays constant during this state change. Okay, so let's plug everything we know into our equation. We have 50 grams for our mass, and we're going to multiply that by the heat of vaporization. So if we go back, remember the heat of vaporization is 2,260 joules per gram. Okay. So similar to before, our units of grams cancel and we're left with joules. So we have 50.0 times 2,260. So let's plug that into our calculators. Wow, okay, I get a really big number. 113 0.000 joules. So that's 113,000 joules. Okay, let's make sure we have correct sig figs here. So how many sig figs does 50.0 have? 3. So this 0 is significant. It comes after a non-zero digit and a decimal point. And then this 0 is in between those two significant values, so it's also significant. So those are all significant. And then what about 2,260? How many sig figs does that have? Or another question is that last 0 significant? No. So that 0 at the very end of 2,260 is a placeholder 0. There's no decimal point there, so it is not significant. So this also has 3 sig figs. Okay, so our final answer then should also have 3 sig figs because we're multiplying. So if we look at our value, it already has 3 sig figs, so that worked out. That was super easy. We've got 113, and then the last 3 zeros are placeholders, so they're not significant. So this also has 3 sig figs. Now, remember, we're not trying to find an answer in joules, we're trying to find an answer in kilojoules. So we have one more calculation we need to do. Okay, so let's set up our next calculation. We're going to convert joules to kilojoules. So I'm going to set up a conversion factor. Oh, there we go. And I want to convert to kilojoules and get rid of joules. So how many joules are in 1 kilojoule? 1,000. Okay, so for every 1 kilojoule, there are 1,000 joules. Okay, so let's make sure our units cancel. We have joules in the numerator and the denominator. So we'll end up with kilojoules. So really, we're dividing 113,000 by 1,000. So that should give us 113 kilojoules. And that has 3 sig figs still, so that works out. Okay. So sometimes, again, it's easier to express your final answer by using a prefix in front of your unit, because then, for instance, you don't have to write out all of those zeros. Instead, you can just write it as 113 kilojoules. And here are the solution slides. So let's summarize everything we learned. So we saw that a solid can turn into a liquid, and a liquid can also turn into a solid. We also saw that a liquid can turn into a gas, and a gas can turn back into a liquid. So if we're going from solid to liquid, what is that process called? Melting. What if a liquid is turning into a solid? What is that process called? Freezing. What if a liquid is turning into a gas? What is that called? Vaporization. Or boiling. Either one's fine. What if a gas is turning into a liquid? What is that called? Condensation. Okay, and then remember, a solid can also turn directly into a gas, and a gas can turn directly into a solid. So what do we call the process of a solid turning into a gas? Sublimation. And what if a gas is turning into a solid? What is that called? Deposition. Although deposition sometimes reminds me of some of those law shows I watch, but it's different. Okay, so then we also learned about heat of fusion, and that was the heat needed for melting or released during freezing. And we also learned about heat of vaporization, which was needed for vaporization or boiling and released during condensation. Okay, so another thing to remember too, when we talked about solids versus liquids versus gases, we said that solids had particles that were really, really close together and very rigid. We said liquids were, the particles were also really close together but could move around. And then gases, the particles in a gas are really far apart and very energetic. And that makes sense when we think about how much heat is required to turn a solid into a gas or turn a liquid into a gas. So gases have a bunch of energy. We've put a bunch of energy into those particles. Okay, so next time we're going to talk about heating and cooling curves. So these are not really curves because we have mostly diagonal and flat lines in them, but this can help us to organize some of the information we just talked about. So we'll go over that in the next video. I will see you then.